You just heard a digital audio compressor running in firmware on this STM32 based digital guitar effects processing platform. In this video, I'd like to go through the basics of compressors, show an example design in its block diagram architecture of a compressor, going through the individual blocks that make up a compressor, their function and purpose, and then finally how to implement that on a real-world system on an STM32 based microcontroller, and we'll be processing audio in quasi-real time on this custom platform and implementing our audio compressor. At the end of this video, then we'll do some tests, both looking at this on the scope with a WaveGen and then also playing some guitar through this briefly. A huge thank you to JLCPCB for sponsoring this video. I had these digital guitar effects PCBs manufactured and assembled by JLCPCB, and they did an absolutely fantastic job. JLCPCB is super easy to use. All you have to do is go onto their website at jlcpcb.com, click on Instant Quote, upload your Gerber data and select options, and you of course can select PCBA as well, and they have pretty advanced manufacturing and assembly capabilities. Not only is JLCPCB very easy to use, but they are also incredibly affordable. For instance, 6-layer PCBs at 50 by 50 millimeters, 5 of them with an Enig surface finish, epoxy filled and capped vias for only $2 and only 5 to 6 days is incredibly affordable, and currently also have up to 8 layers for just $2. I've placed a large number of orders, both PCBs and PCBs with assembly at JLCPCB, and so far I have had next to no issues. They're very reliable as they have an all in-house production and very rapid turnaround. Even with assembly, I can typically have my boards back in about 1 to 2 weeks, which is pretty amazing. Links will be in the description box below. Another huge thank you also to Altium for sponsoring this video. If you'd like to give the powerful Altium 365 platform a try, make sure to follow the link in the description box below, or go to altium365.com/YT/Phil's Lab, and you can get yourself an Altium 365 free trial. Altium 365 brings many impressive features to Altium Designer, such as collaborative design, design reviews, mechanical co-design with SolidWorks, Fusion and more, manufacturing collaboration, easy bill of material management, and much more. If you'd like to check out in part some of the cool Altium 365 features, make sure to go to my GitHub profile or go to pms67.github.io and check out some example hardware designs that were shown on the YouTube channel and also for this particular video. You can check out a couple of the boards, for instance the Queen Bee controller for the micro quadcopter using the Altium 365 viewer. You can check out the schematic, PCB, look into all the routing and all of the layers in real time, and also of course check out the 3D view, which I think is super useful, especially when you're sharing designs with people maybe even outside of your organization. I'll leave links in the description box below, and thanks for checking them out. Before we start going into depth into how to implement a compressor, let's briefly go over the very basics of audio compressors. In essence, compressors or dynamic range compressors take an AC input signal, such as some sort of audio source, this could be vocals, guitar, or a complete mix. The compressors take that input signal and, very simply speaking, multiply it by a calculated varying gain to control its dynamics. By multiplying by this gain, we can change the final amplitude of our signal, and we can change that on the fly. So this is not a static multiplication. We increase or decrease the amplitude based on certain characteristics and settings. Compressors are very useful, and they're used everywhere in the recording world, for musical instruments, guitar, and so on. And they're often used to reduce the overall dynamic range of a signal or audio source. This is for regulation, for volume control, might even be used for artistic effects. Oftentimes compressors sound somewhat invisible, but depending on their settings, you can quite clearly hear when an audio source has been compressed. In essence, loud signals and quiet signals are brought closer together in amplitude, which can help with controlling that audio source, especially when you're mixing or when you want to fit in with other audio sources. For example, I'm compressing the audio in this video to make sure that when I speak loudly or quietly, this does not affect you and you're getting an approximately similar amplitude overall throughout this video. For compressors, there are of course many different types. There are studio compressors, guitar compressors, and much more. There are quite a few controls to adjust the behavior of the compressor. Oftentimes you'll hear threshold, ratio, attack, and release times, and compressors do vary in their capabilities. For instance, on the bottom right-hand side, I've shown two compressors. One is a very popular SSL G-comp compressor, which is typically used on recording consoles. It has a display for the amount of gain reduction or compression, threshold knobs, makeup, attack and release times, ratio, and a high-pass filter. Whereas on the far right-hand side, this is a Walrus Audio Mirror, which is a guitar effects compressor, so specifically for guitar frequencies and for guitar amplitudes and signal levels. And that also has some similar controls, such as threshold, ratio, but also has different controls as well, for instance, a blend. So not all compressors are built the same. They're built for certain audio sources or for other ones with different controls and different architectures, as we'll see. In this video then, I would like to show you how to implement a very basic sidechain compressor in software using digital signal processing on a custom STM32 based audio processing platform. There are many different types of audio compressors. There are many different architectures, and I'd strongly suggest checking out a number of different books and papers on this topic, and I'll leave some links in the description box below. Typically, if you want to implement something in DSP or in software or in firmware, we might take an analog prototype, we might look at an analog circuit and see how we can emulate that in software. So that's definitely one way of doing it. If you look at analog prototypes of compressors, they might be based on voltage-controlled amplifiers, they might be optical compressors, and so on. In our case, we will be designing a very simple sidechain compressor, which is shown in the block diagram below. Keep in mind, this might look terribly overwhelming, but we will go through each individual step of this block diagram, explain the purpose behind that particular block, and then how we can implement that in software. Again, this is a very generic compressor. The basic structure of compressors are fairly similar. We want to take a look at the input signal, and this time we are in discrete time. That's why I've denoted everything with sample numbers. So for example, x of n is the nth sample of our input, where x is the input. Our compressor takes a look at the input signal, sees what instantaneous amplitude it is at, does some computation to provide some sort of gain at the output, and multiplies that input number x of n with some sort of varying gain to give us an output y of n. The way this gain is calculated depends on various parameters that we set. That could be thresholds, attack and release times, ratios, and so on. In essence, telling the compressor when to engage, when to disengage. For instance, if we are over a certain input amplitude, we might want to reduce the gain at the output to lower the overall signal volume y of n. This block diagram shows a very simple way of doing this, and this is a very simple sidechain based compressor. We have one forward path where x of n pretty much is just fed through to the output and multiplied by the gain, and we have this bottom path which is known as the sidechain. I've also shown a delay in the forward path, so x of n passes through this delay, and this can be used to compensate for the delay introduced by the sidechain to make sure the calculated gain aligns approximately in time with the samples that were used to calculate this gain value. In this video, we will not be implementing this delay, but do keep this in mind that this could be an option. So for us, imagine there's just a straight feed-through line, xn, to the multiplier or mix on the right-hand side. What's interesting for us then, of course, is not just the multiplication. That's very easy. We just do xn times the gain is y of n, but how do we actually compute this gain? The first part is an envelope detector. That feeds into a gain computer, which has various parameters such as threshold, ratio, and knee width. That computed gain by the gain computer is then smoothed based on attack and release times, and we'll go into depth what that is. That gets added to a makeup gain, and then we get a final gain that is multiplied with the input signal to produce the output signal. Now let's see every block in detail and why a compressor does what it does. First of all, starting off with the envelope detector. Our AC signal might look something like the image shown in the middle right on this slide. For audio, we typically have frequencies from around 20 Hz up to 20 kHz, so fairly rapidly time varying, and we want to calculate the envelope, or rather the instantaneous amplitude shown in red of this incoming AC audio signal. For our compressor then, if our instantaneous amplitude, this curve that follows the overall envelope of our signal, is above a certain threshold, we want to reduce that amplitude or compress it, reduce the gain of that signal. To compute this envelope, there are of course many different options. For instance, we could just not even compute the envelope, we could just do an absolute value of our current input waveform, so abs of x, we could do a peak envelope detector and so on. But in our case, we will be doing an RMS, so root mean squared envelope detector. I won't be going into detail how to implement this, but this is because I've already shown this in a video. This is video number 103, which shows a recursive method of computing the RMS for discrete time digital systems. After you watch that video, you will see that we have a window length for this recursive RMS. We are only looking at a certain window in time. And the question is, how do we determine that length? And that, of course, might depend on the minimum frequency in our signal. So for audio, we might want to look at 20 Hz as the lowest frequency, which would give a 50 millisecond time window. But of course, if we have longer window lengths for our recursive RMS, that will introduce that amount of delay. So for look at 20 Hz lowest frequency signals, we might get 50 milliseconds of delay in our RMS computation. So of course, there's some sort of trade-off. But in essence, for our envelope detector, all we want to do, again based on video number 103, is implement this formula in red. Once we've computed our envelope using this recursive RMS, we convert this envelope value into decibels and then feed it into the next stage, which is known as the gain computer. And the formula for converting into decibels is simply taking 20 times log base 10 of our linear input signal. Now I've added a small plus epsilon term, so this might be a very, very small number, something like 10 to the minus 9, something like 10 to the minus 12, because our input signal in the case of this digital system ranges from +1 to -1, and of course we're taking the absolute value, but of course passing it through the RMS detector makes this into a positive only number, but it could also include 0. And if we take a log of 0, that is undefined, so therefore I'm adding a very small offset, this epsilon term, to make sure we don't get an erroneous computation. We'll see this in code later as well. Our envelope or our instantaneous amplitude is fed into what's known as a gain computer. Very simply speaking, the gain computer is nothing but a static nonlinearity. For a given input amplitude, the gain computer computes a certain output amplitude, and with that, so the ratio of output amplitude to input amplitude, that gives us the gain, which in turn later down the chain of this compressor will attenuate the signal by a certain amount. The gain computer has several controls. These controls could be more or less, but these are fairly typical. One is the threshold in decibels. That's asking above what input level does the compressor engage. Then we have a knee, which is known as a transition between the uncompressed and compressed region. And knees can be hard knees or soft knees, and I'll show you the difference in just a second. And then we also have a ratio control, which is when the compressor is engaged, how much are we compressing the signal? By what amount? By what ratio? This is visualized on the graph on the right-hand side. On the x-axis, we have the input amplitude in dB, where our maximum input amplitude is 0 dB, so this is a relative dB scale. And the y-axis shows us the output amplitude, also in dB, with a maximum value, again, of 0 dB relative. We have two main regions for this hard knee graph, and they are separated by this threshold value. The threshold here is drawn in at -40 dB. So with an input amplitude of below -40 dB, so -40 dB or less, we are not applying any compression. Our output signal is equal to our input signal. It's simply a linear straight line. Above the threshold value, so in this random scenario, above -40 dB, we move past the knee, which is at the threshold, into our compressed region on the right-hand side. We are now in the compressed region, and this is where the ratio setting tells us by how much our input signal is attenuated or reduced to give us an output signal. So for instance, at an input signal of -20 dB, we might be at -35 dB out. So we've reduced it by 15 dB relative. I'll show you a soft knee in a second, and I'll also play around with the parameters using a graphing calculator. But before that, again, these dBs are relative to whatever your system amplitudes are. If you're doing it relative to 1 volt, RMS, if you're doing it relative to a certain peak-to-peak voltage, and so on. In our case, I'm being a bit vague with dB because, again, dB in my case is relating to a full-scale input signal. So it's 0 dB full scale, which in my digital world is ±1 as a floating point representation. We can use a graphing calculator to plot these various regions of our gain computer. And these formulae I've taken from some popular literature, and this is what we'll be implementing in our C code in our firmware later on. In essence, we have 3 regions. The red part is our uncompressed region, so when signals are below a certain threshold. Then we have this knee shown in black, and above the knee we have our blue line, which is where we're in the compressed region, where our ratio control dictates the slope of this final part. We can see here the knee is not just a single point anymore, and this is a smooth curve, so a transition between uncompressed on the left and compressed on the right-hand side. This is what's known again as a soft knee, and I can change the knee width, which is indicated by W on the left-hand side, so I can increase my knee width, and you can see that black region, that transition region, is now expanding and giving us a softer transition. If I change my knee down to 0, my knee width down to 0, you can see this is now a hard knee. It is a single point transition. Oftentimes, compressors are favored with soft knees, and that's what we'll be implementing, but you can implement a soft knee and simply set your knee width to 0 to give yourself a hard knee. And of course, this changes the sonic characteristics and might be less aggressive of a compression. Other than the knee width, we can of course play with the threshold. Right now the threshold is at -30 dB. I can increase the threshold, which gives me a larger uncompressed region, or I can reduce the threshold, which means the compressor starts engaging earlier. Then the ratio, as we said before, controls the slope of the compressed region. So if I increase my ratio, let's say to 10, this line, this blue line gets more shallow. We are heavily compressing the signal above that threshold, above that knee. If I reduce the ratio down to 1, we can see we're not getting any compression at all. Our input signal is equal to our output signal. So typically, of course, we will have a number larger than 1 for our ratio. After the envelope has been computed, fed into the gain computer, we now have a specific gain value, one number, that is then passed into the attack and release system of our particular compressor. The attack and release are used to smooth this gain, because at every sample time we are recomputing the gain, and we might get very, very sharp jumps between them, and we might not want to have the compressor engage or disengage that quickly. Therefore, we have attack and release. So we take the static gain computed by the previous stage, that gain computer, and we smooth it. And if you think of smoothing, we should always think of filtering it. There are two scenarios. One is if the static gain is less than our current smooth gain value, so the value of the output of the filter, then we are in an attack stage, because the static gain is saying it's lower than the smooth gain, which means you need to reduce the gain, and which means the compressor engages. This is our attack stage. On the contrary, if the static gain is greater than our smooth gain, so our new computed value is greater than our filtered value, the compressor now disengages, and we are in the release stage where we're increasing the gain. This is shown on the right hand side in this image for a certain input signal, which is below the threshold initially, then input signal amplitude increases, is now above this blue line, this threshold. This means we are in the attack region, and the compressor gain ramps down to a smaller value below unity, which in turn over time in this attack stage reduces the output signal amplitude. Then once the attack time has passed, the filter is no longer changing its output value, and we are still above the threshold in the input signal. After that time, we're now seeing that the input signal now goes back below the threshold, so the compressor should disengage, and we are in the release region. So the compressor ramps its gain back up to unity, and we are no longer attenuating over a certain amount of time the input signal, so our output signal grows again. And we can see here we have two different times. One is an attack time and one is a release time. In this setting, our attack time is quite a bit shorter than our release time, and this might be typical for compressors. Attack and release filters will have different time constants, can have different time constants, but can also be the same. Again, the attack and release times determine how quickly the compressor engages or releases or disengages. And for instance, setting the attack time longer will help passing initial transients, so the compressor doesn't clamp down if you're trying to let the transients through. Typical attack times might be something in the order of a couple of milliseconds, and release might be something as long as a second. If we think of implementation, we have our static gain, we want to filter it. The easiest way to do this smooth exponential ramp is by using a first order IIR low pass filter. We think of an RC low pass filter analog prototype, a simple resistor in series and a shunt capacitor. This gives for step input an exponential rise and an exponential fall time. Thinking back to our basic electronics theory, our rise full time for this RC network from 10% to 9% of amplitude is approximately 2 times R times C. I have a video on IR filters on my channel. I'll leave that in the description box below, but very simply, jumping ahead, the discretized equation is shown below. The smooth gain at sample time n is a filter coefficient times the smooth gain of the previous sample time plus 1 minus the filter coefficient times the output of the gain computer, the static nonlinearity. The filter coefficient can be computed approximately using this rise full time relationship, so it's e to the minus 2.2 divided by the attack or release time times the sample rate, because we are in a discrete time system. So very simple first order IIR filter for attack and release. Now keep in mind, you could of course include your attack and release times in the envelope detector, so how quickly that engages, but for a very simple demonstration I've put it as a IIR filter after the gain computer. Again, there's many different structures to compressors. We're almost at the end of our block diagram. All that is missing now is the makeup gain and then the final gain adjustment. So I'm multiplying our input signal with our computed gain to give us the output signal. Oftentimes compressors will have a makeup gain, which is added after the smooth gain to compensate for the overall volume reduction. If we have a very low threshold, or if we have a lot of ratio, so a high compression amount, our input signal's amplitude will be reduced considerably because of the gain. So oftentimes we add a static makeup gain to the output gain. We can also auto-compute the makeup gain, and this is based on the threshold, knee, and ratio settings, and for 0 dB full-scale input typically. In our implementation, we will just do a user-controllable makeup gain. Once we have the makeup gain added to the smooth gain, so after the attack and release filters, this gives us the total gain in decibels, and this value in decibels is converted back to linear, because then this linear total gain G can be multiplied with the input signal to give the compressed output signal Y. And again, this happens at every single sample time, at every single sample step. So overall, we've taken this block diagram, dissected it into various different parts and shown what every individual part does, and now we can implement that. Again, this delay line at the top we will not implement. It'll be a straight feed through from x of n to the multiplier with our gain to give our output y of n. Now let's go through the code which I've already written for the sake of time and see what basic elements we need to implement for a compressor which we just saw in block diagram form. I have a .h and a .c file for the compressor to separate with some various defines and constants, for instance specifying the RMS window length in milliseconds, what minimum maximum thresholds, knee widths, ratios and so on we have for this particular compressor, and for this I've used fairly typical ranges, fairly typical values, which you can of course tune for your particular system. Then I have a couple enums just to define what detector we're using, if it's an instant or peak or RMS, and if we're using soft or hard knee. Then the main struct that contains all the compressor variables is this IFX compressor struct. Again, just noting down the detector knee type. I have a moving RMS implementation, again from video number 103 in my channel. Then the various compressor settings, threshold, knee width ratio, attack coefficient and release coefficient. So these are pre-computed coefficients for the filters rather than the raw attack and release times in milliseconds. So these are pre-converted so we don't have to compute them every single cycle. Then makeup gain, various gain calculations, and the final compressor output. In terms of functions, we have an initialization functions just to compute and clamp the various parameters of this compressor, initialize the various variables, our main update function, which takes our latest input sample, produces an output sample, and then all the parameter setting functions, all the parameters we just saw. Briefly looking at the parameter setting functions, all I'm doing is I'm taking the parameter as an argument and my compressor struct by reference. I'm checking if the argument for that parameter is within the bounds we set, so minimum and maximum, and then passing that bounded threshold or parameter to my compressor struct, and that's all I'm doing for all of these other parameter setting functions. With exception for, of course, the attack time and release time. The attack time takes as arguments the compressor struct by reference, as well as the attack time in milliseconds and the system sample rate in hertz. I clamp the attack time in milliseconds, and after that I pre-compute the attack coefficient as we saw from the slides earlier. That's simply taking e to the minus 2.2 divided by the attack time in seconds times the sample rate in hertz. So the 0.001 times attack time milliseconds is simply a 2 seconds conversion. That's all we're doing. Similarly, for the release time, it's the same thing, except it's for the release time and the release filter coefficient. Jumping up to the initialization function takes in all the parameters that I need to set up my compressor. We initialize the moving RMS. This will be the basis of our envelope detector, and I pass as an argument the length of the window I want. In this case, I would like 50 milliseconds of window, which corresponds to a 20 hertz cycle time. And that's all I'm passing as an argument here. I'm setting up the detector knee types, and I'm calling the functions we just saw to set the parameters correctly, and I'm initializing the gains to 0. The main part of the code is now, of course, in our update function. Again, we take our input, our current input sample, and we produce our current output sample. And all we're stepping through now is our block diagram. So let me pull that up side by side. The first thing we have to start off with is our envelope detector. And all we're doing for this, in my case, I have the option for instantaneous just to try this out, and the moving RMS envelope detector. So I'm passing in my input sample to the moving RMS, which returns the output sample, which is my computed moving RMS. Now keep in mind, this moving RMS function actually returns the square, not the square root of the moving RMS. So you can, of course, adjust your 0 dB, your relative dB ratios to match the actual system voltages. For this, I haven't bothered, so my dB is rather vague. As we talked about before, I'm also adding this tiny term so I don't get a 0 value in my logarithmic calculations, so 1e minus 9, 1e minus 12, something like that. Taking the base 10 logarithm and multiplying by 20 to get my input envelope in decibels. After the envelope detector, which is just the RMS and calculated dB values, we're jumping to the gain computer where we have these various regions. Depending if you're doing a soft knee, hard knee, I will show you how to do a soft knee. So we have 3 different regions as we saw in the graphing calculator. We have this no compression region, this red region, we've got the black soft knee region, and we've got the compressed region, which is this blue region. And I'll link this in the description box below, but I've taken this from the MATLAB MathsWorks site, looking at their compressor implementation. And for a soft knee, you have to follow these 3 equations, given these 3 ranges. So if the input level is below this threshold minus half the knee width, you simply set output is equal to input, and you have these other 2 sections in this 3-part graph that you implement for a soft knee. This is all I've taken over and implemented in the gain computer for this soft knee. So I have these 3 regions, 3 sections to this if statement, implementing our gain computer. For a certain input in decibels, I'm producing a certain output in decibels. Once you have the input and once you have the output, that ratio of those is, of course, the gain. And because we're working in decibels, that ratio turns out to just be a difference. So out minus input, when we're working with logarithms, is the ratio, so that is the gain. After the gain computer, we look at the attack and release times. And these are simple first-order IIR filters, but they're conditional, for lack of a better word, IIR filters. If the static gain is less than or equal to the smooth gain, we're in the attack stage. If the static gain is larger than the smooth gain, we're in the release stage. And this is all I'm doing here with this if statement, and I'm computing the IIR filter as we saw mentioned in the slides, that the smooth value is the attack coefficient times the smooth value of gain, so the previous filter output, plus 1 minus the attack coefficient times the current computed gain from the output of my gain computer. And similarly for release, if we happen to be in the release stage. Once we've smoothed the gain, we can add our makeup gain. Because we are in decibels, we don't have to multiply, we are adding. So we're adding the smooth gain, the filter output, to our makeup gain constant, or rather variable, because we can change it as the user. After we've computed the final gain, in decibels, we convert that to linear. So to do that linear, we take 10 to the power of the gain divided by 20 to invert from decibels to linear. Once you have the linear gain, I'm just simply clamping it. So if the user has a very large makeup gain, I don't want the linear gain to be above 1 or the decibel gain to be above 0 dB. Then all I'm doing, this is the final compressor step, this is our multiplication. I'm taking my final linear gain, timesing it by the current input sample, and that is my current compressed output sample. And then I'm returning that. And that's all there is to this compressor. And that's why I quite like this block diagram form, because then implementing it in software is fairly straightforward. We have all these individual blocks and we can cascade them in code and combine them as necessary. In terms of main.c, actually using this compressor, I of course have to include my compressor header file, create my compressor struct. I initialize the compressor with some rather default values using the RMS detector and a soft knee, and passing through my sampling frequency of my system. And then in the processing callback function, so for my I2S audio streams, I'm looping through each individual sample, converting each sample to a float with maximum values of plus minus 1, calling my compressor update function with my raw sample, clamping the output and passing that output to my DAC audio buffer. I'm doing nothing else. Then in terms of controls, I have an asynchronous loop that reads in potentiometer values of this board, and I've mapped certain potentiometers to the various control values. So for the threshold, ratio, makeup gain, attack time, and release time, I can vary those using the 5 potentiometers I have on my board. I can turn on and off the effect using one of the foot switches. So that's pretty much all there is to implementing this compressor. So now let's play around with it a bit and see how it sounds. I now have my Analog Discovery Pro by Digiland hooked up to our digital signal processing platform running the guitar effects processor as we just implemented. The first thing I'd like to show you is just what happens if we inject, for instance, a sine wave and play around with ratio, thresholds, makeup gains, and so on, see what effect that has on a basic sine wave. To do that, I'm feeding the wavegen output of my Analog Discovery Pro into the input of this guitar effects pedal, and I'm monitoring the output of the guitar effects pedal with the compressor engaged on channel 1 of the scope. On the left-hand side, we can see Cube IDE, and I'm doing a live expression view of my compressor structure, of my compressor struct, so we can monitor the variables such as threshold, knee width, ratio, and so on in real time. So with a 1 kHz 1 volt peak sine wave fed in, we can really see we are getting some attenuation with the compressor engaged with these various settings. The threshold is pretty much at a maximum, so close to 0 dB, meaning the compressor shouldn't be doing terribly much because the threshold is very high for compression to begin. The knee width is a constant and the ratio is set to the minimum at 1.5. The attack and release I've set to the fastest values, and the makeup gain is currently at a minimum as well. The first thing I like to do is rotate my threshold control and bring my threshold down, so more negative, that is smaller dB. And we can see as I bring my threshold control down, remember the dB is relative to whatever my maximum signal amplitude is for this particular digital system. But as I bring my threshold down, we can see the compressor is starting to engage and starting to reduce the gain, which we can see in the gain final variable. With the compressor threshold set down and it being engaged, we can now adjust the makeup gain, which is what I'm doing now. So now the compressor is acting on the input signal, but we're restoring some of the gain with a fixed constant amount by changing this makeup gain parameter, so I can play around with that to adjust the makeup gain. And this can be used for compensation. Other than adjusting the threshold, again telling the compressor when to start acting on the signal, we can of course also adjust the ratio. So with the threshold set, let's say at around -47 dB, again the dB in this sense is a tiny bit meaningless, let me adjust the ratio control. So I'm going to increase the ratio from 1.5 for instance to 2 and even higher, and we can see the amplitude of the output waveform is rather squashed more and more. We are reducing the amplitude because we're increasing the ratio of our compressor, we're reducing the slope in our static characteristic, which means we're getting more compression, we are reducing the amplitude, reducing the dynamic range. So those two controls look like they're doing what they're supposed to be doing. We can explore also what the effect of the release time is. Currently I have my release time set rather fast, so right to the minimum at about 1 millisecond. If I set my threshold to 0 dB, that is the compressor isn't engaged, if I then increase the threshold and then quickly release it, that time it takes to release or go back to the compressor being disengaged shows us the effect of the release time. So right now the release time is very quick. If I flick my threshold back to 0 dB, we can see amplitude jumps back to its maximum value very quickly. But now if I increase my release time, I'm going to increase it to maximum. That is about 1000 milliseconds, so 1 second, and I do the same thing again. So I'm going to turn my threshold down and I'm going to quickly jump back up again. We can see it's a far slower rise or release due to the filtering or this gain smoothing. So again, turning the threshold down, the compressor is engaged. If I change my threshold back to 0 dB, we can see it's a much slower release of the compressor. Now with the attack time, because we've set rather short ranges, so 1 to 50 milliseconds, we could of course demonstrate that in the other direction, but it's rather hard to see because we only have 1 to 50 milliseconds. So that's why I've just demonstrated it with the release time, but I hope that shows you what is happening behind the scenes. Thank you very much for watching this video. I hope it was useful and I hope it showed you the basics of implementing your own audio compressors or dynamic range compressors in software and in DSP on, for instance, STM32 microcontrollers. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest DSP, firmware, hardware, and embedded systems videos. Thanks again for watching, and I hope to see you in the next one. Bye bye.